this chapter, we will be looking at logarithms. In this specific lesson, we'll be looking at the characteristics of logarithmic functions.
All right, well, everybody, in this chapter, we're going to be introducing a brand new function called a logarithmic function. Okay, and you're going to see that these are actually really incredible tools to have in your arsenal when you're attacking problems. In the last chapter, when we were looking at exponential functions, there was a point where, when you were working with exponential equations, where you got stumped. Okay, where as long as the exponential equation was set up nicely, I could solve it algebraically. But if it wasn't, then I'd have to go through and use a graphical solution. But logarithms allow you to get around that problem here. Okay, so here we're going to just zoom in a little bit and work our way through this. So to start off with, the logarithm function is the inverse, which makes it the mirror image of the exponential function, okay, that we just finished studying. Okay, now when we say mirror image, it's really, I hope you got to understand this, that when we talk about the inverse, so here's the exponential function looking like this. Okay, when we talk about the inverse, it's actually a reflection. Okay, this is, when it says mirror image, this is over y equals x. The mirror is along that line right there. And when you reflect that over, you're going to get a function that looks like that. And right here, this is your log graph. Okay, your log of x there. Now I got to get a little bit more detailed about the notation, but yeah. So this is your, for example, some base to the x, and this is your log base b, and I'll talk about that in just a second there, log base b of x. Okay, so it's the inverse of the exponential function. That's what it says here. Now let's just think about what else that is saying. Okay, because it's the inverse of the exponential, let's throw down an exponential here, a really simple one. Y equals b to the x. Okay, now the inverse tells me to swap the x and the y. So x is going to equal b to the y. That's an inverse. Okay, as soon as we do that, we found the inverse of this original function here. Except that normally when we find inverses, the first thing we're going to do is isolate y. We'll get y equal to whatever. Okay, we're going to figure out what the function is. Now, at this point, prior to having logarithms, there was no tool for doing that. Logarithms are actually invented to fill that little hole there. Well, not specifically. They were invented for another reason, but essentially to deal with this right here. So what we do here is, this is now equivalent to, okay, we come up with exactly the same form here, an equivalent form, where y is equal to, so here we go. Okay, so x equals b to the y. This is the inverse of the exponential function. This is a logarithm. Okay, that's exactly what that is. It doesn't look like it yet, but that's what that is. Here's the equivalent form that we're going to get more comfortable with. Y equals, so notice that what I'm about to build here belongs in the exponent here. Okay, and the way we do it is this: we throw a log, log, and the log has a base. Okay, we put a little subscript down there, a subscript b, and the bases are the same. And then what we do is we write the x here. So x equals b to the y is the same as y equals the log base b of x. Okay, they are identical. They are the exact same thing. There's just two different forms of writing the exact same thing. Okay? So, down here, a logarithmic function is written in the form y equals a. Now here, they've just thrown a little coefficient out front. Okay? It's just a stretch factor, if you will. Some multiplication up front there. But it's still the log base b of x. Same sort of thing. Now, here's some information here that you absolutely need to know about logarithms. Okay? First of all, where x is greater than 0. Now, if you look back to my little graph over here where I told you that this was the reflection through the line y equals x, remember that an exponential function had the range y is greater than 0. Well, when you perform an inverse, you swap the x and the y. And so now the log function here has a domain. X is greater than 0. So it has to be that x is greater than 0 here. But x can be any real number greater than 0. Okay? The base, the restrictions on the base are basically the same here as they were with the exponential function. It's going to be greater than 0, and we're not going to let b equal to 1. Okay? So now let's just zoom out a little bit here. That's a little bit of an introduction. We're going to kind of embellish this a little bit more as we go along through this lesson here. So to find the inverse of any graph, you switch the x and y coordinates. We've been talking about that. And the line y equals x as a mirror image. So here we go. So let's take a quick look at a very specific, whoops, whoa, wrong way. A very specific example here. This is the function here, y equals 2 to the x. And so what we're going to do is we're going to swap the x and the y coordinates. We've got some key points along the way here. So we've got the point 0, 1, which will become the point 1, 0. Okay, because we're going to swap the x and the y. The point 1, 2 is going to become the point 2, 1. The point 2, 4 will become the point 4, 2. The point 3, 8 will become the point 8, 3. And then you can already sort of see, whoops, gee, I did that badly right away. The pattern forming here, this is going to ride along the y-axis till it gets up to here, and then it's going to swing out like this. And so this will now be y equals the log base 2 of x. Okay, log base 2 of x. And even just swapping the x and the y coordinates, you're going to see this little pattern here. Notice that it is the reflection through the line y equals x. So here's your exponential, here's your logarithmic function here. Now, we're going to take a quick look. We're going to take a look at the properties, okay, of the exponential function. Notice its domain is all reals. Its range was greater than 0. It doesn't hit the x-axis. It's got that asymptote there, right? Okay, it's got that line that it approaches without ever getting to. We call that horizontal asymptote. Guess we might even say this. We've got a horizontal asymptote at y equals 0. It's just that line that if you come over here, the graph gets closer and closer and closer to the x-axis, just never gets there. X-intercepts doesn't have one, but it hits the y-axis at 1. Now, zoom out just a little bit. Our logarithmic function, okay, that consists of these points here, its domain is going to be x is greater than 0, which is a property it kind of steals from the exponential function. The range is going to be all reals. Okay, now you can see it kind of here in the negatives here. This logarithmic graph swoops up, it goes through that bottom half, then it gets to the x-axis and it turns, and then it starts to slowly rise here. Now, this will go off to infinity, but it does it incredibly slowly. It does this very, very slowly, okay? Now, by the time, for example, for this particular graph right here, the y-coordinate here only gets to 10 when your x-coordinate is out past 1,000. Okay, logarithmic functions tend to grow really, really slowly here. The x-intercept here is going to be 1, and it won't have a y-intercept. And again, the reason for this is because this has got a vertical asymptote. Okay, this line that it approaches, it doesn't get to it, but it approaches. And this is going to be at x equals 0. That's going to be the y-axis there. Okay, because the logarithmic graph gets closer and closer and closer to it. Now, if you want to see how to graph these things, I'll show you on your calculator here. Okay, we're going to use just a little trick here. Whoops, wrong way. If you wanted to plot y equals log base 2 of x on your calculator, what you would enter in here would be log of x divided by the log of 2. Okay, because if you look on your calculator down here, you actually do have a log button right there. Now, we should talk about that a little bit here before we get into this. And there's just a discussion here. When you've got just the log of x, if they don't write the base down, okay, because I've already expressed a few minutes ago that you need to have a base. Okay, a logarithm has a base, and it shares the base with its corresponding exponential function. Remember, the logarithm is the inverse of the exponential. Whatever that base is, they're going to share that base. So if you write it and you don't specify the base, then we call this a common log, and the assumption is that it's base 10. Okay? And the reason why it's base 10 is because fingers. Okay? 10 is just an extremely useful number for us to work with. We got 10 fingers, or 10 digits there. Anyway, 10. So log base 10 of x is the same as the log of x. Okay? You just don't write it here. So now if you go back to your calculator and you want to graph something like this, what we do is we take remember, this was equal to the log base 2 of x. We take the common log of x and divide it by the common log of 2. So I'll show you here. We'll go y equals. Okay, I'm going to clear this up. That's from some older work there. And so I would type the log. Remember, I get that from right here, right by the 7. Okay, the log of x divided by the log, where am I at here? Log of 2. Okay, press enter. And now I'll go zoom standard here to go back to my zoom settings, and then there's my graph right there. Okay? And in fact, you could do this with anything. If you had, for example, if we had the log y equals, the log, I don't know, let's make it the log of 5 of x, then what we would do is we would make this the log of x divided by the common log, the common log of x divided by the common log of 5. And in fact, let's do that just to see that, how they compare. So y equals, we'll come down here, we'll make this the common log of x divided by the common log of 5. If I graph that. Okay, now notice what happened here. You can't quite see it along the y-axis because it goes really closely here, but if you look at this, that little bit right there, the graph is closer to the y-axis. They both go through 1, and then this one is closer to the x-axis. Now, if you think back to what exponential functions look like when we changed the base there, okay, when we made the base larger, the exponential function did an almost identical thing. Okay, it rides along closer to the x-axis, and then when it crosses the it rides along closer to the x-axis, and then when it gets to the y-axis, it shoots up faster. Right? So it looks something like this. Here was your regular one, and then when you increased the base, it shot up like that. So we're seeing a very, very similar behavior with logarithms. And that's to be expected, okay? Because they're related. A logarithm is an exponent. In fact, that's probably worth writing. Let's come down here. Let's write this down here. A logarithm is an exponent. Okay? A logarithm is an exponent. You really want to catch that, okay? Because we're going to see some rules for logarithms in a bit here, and they're all based on the fact that a logarithm is an exponent. And again, I'll point that out. I'll slide that back up to here to some work that we did. When you have it written as x equals b to the y, remember that the way we convert that is y is equal to log base b of x. Okay? Y equals a logarithm. Well, y came from the exponent. Y equals a logarithm. So that logarithm belongs in the exponent. Okay. So just at the bottom of the page here, just another little note here about common logs. So the graph y equals the log of x is a reflection of the graph y equals 10 to the x about the line y equals x. Okay, they are inverses of each other. So just so that we can see everything here, this is y equals 10 to the x, and there's your common log of x, inverses of each other. All right. Now we're going to look at some more information. We're going to do some questions here.
Graph the following functions in your calculator and then fill in the following table.
Okay, so for this first one that we're supposed to graph, it's y equals the log of x. So we're going to go to our calculator. Okay, y equals the log of x. And I've just got standard zoom settings there, so let's just press that graph here. Now this is base 10. Okay, if it's not written as base 10, and oh, that thing hugs the x-axis pretty strongly here. And you're not seeing it here, but it does. It rides along the y-axis there. So this graph is going to look, something like this. Is that really, really close? Now, the domain, it doesn't even touch the y-axis. It gets close to it, but doesn't. So the domain here is x is greater than 0. The range is going to be y is an element of the reals. It will go up. It's gone down infinitely, and it will go up infinitely. It just does it really, really slowly. X-intercept. Okay, well that's going to occur at 1. Okay, and actually that, if you think about it, that makes perfect sense here. Now let's just talk about that really, really quickly here. So I've got y equals the log base 10 of x here. Now for the x-intercept, I make y equal to 0. So 0 is equal to log base 10 of x. Now remember what we had seen previously. In fact, I'll write it up here. When we had y equals b to the x, that was the same as, or actually, sorry, I wrote it a little differently, and I'll be consistent with what I wrote just a few minutes ago. Okay, we had x equals b to the y. This was the same as y equals the log base b of x. Okay, so there's a beautiful little comparison here. Y is equal to, the logarithm is the exponent, the bases are the same, and whatever the power equaled, that's what you're taking the log of. So right here, for example, I can convert backwards. So I've got a base of 10 here, and I've got a 0 on the other side, so this would be the same as 10 to the 0 is equal to x. I'm just going backwards with this model right here. Okay, so right now I've got 0 equals log base 10 of x, which means x must be 10 to the 0, and actually 10 to the 0 is just 1. So there's my x-intercept. I made y equal to 0, and when I solved for x, I got 1. So the y-intercept is 1. Sorry, the x-intercept is 1. Now the y-intercept doesn't exist because I never actually touched the y-axis. Okay? Now let's see what happens when you do this. What if we take that common log and we multiply by 10? So now I've already got the common log in here. So to put a 10 in front, what I'm going to do is I'm going to put my cursor right there, and then I'm going to press second delete to access the insert that's just above it. And so what that does, the calculator is now waiting for me to type something, and whatever I type, it's going to put in front. So 10 log x here. So now if I press graph, okay, so now what that's done here, notice it's really stretched that out. Instead of it being so tight to the x-axis, now this thing looks a lot more like this. Okay, well, it's kind of neat. You can see more of it. However, it didn't alter the fact that x is still greater than 0 for the domain. Okay, it's still not going to cross the y-axis here. The range is all reals. Now have a good look at that again. What's the x-intercept? It's still just going through 1. It's still just going through 1 here. Multiplying by that 10 really didn't mean anything. And now that makes perfect sense here too, though, because if I make y equal to 0, and now divide by 10, because I want to get x by itself, I'm going to try to isolate the x there. The first thing I would do would be to divide by that 10, and then I'm right back to where I was in that the previous part of this question. So yeah, it makes sense that my x-intercept here would be 1. And again, we don't have a y-intercept because we don't touch the y-axis. Okay, so y is equal to log base 1/5 of x. Now think about what we did previously here. If I want to graph this, what I'm going to sketch here will be the log of x, the common log of x, log base 10, because that's on my calculator. And then think about what we were doing before. I'm going to take the log of 1/5 here. I'll divide that. So the log of 1/5. That's the pattern here. It's actually called the change of base rule. Okay, if you've got y equals log base b of c, this is the same as the log base a of c over the log base a of b. You can convert it to whatever base you'd like. Now for us, it makes sense to convert this to what we call the common log, base 10, because that's on my calculator. So now I'm going to go back to my calculator here. I've already got that function in there. I'll clear that out. And so we'll type in the common log of x divided by the common log of 1/5. Okay, press enter. I haven't changed the window settings. Let's just see what it looks like. Oh, look at that. Look at that. It's just moving the other direction here. It's doing this. It slides along the y-axis again and then kind of shoots out this way. And isn't that similar to what we saw with the exponential functions? I mean, honestly, if you kind of wrote it like this, you're getting the same sort of motion or same sort of change in motion for the logarithmic function as we got with the exponential function when the base turned from a number greater than 1 to a number less than 1. But just like with exponential functions, the main properties of the graph don't really change. This is still element of the greater than 0. Okay, that's the domain. The range is still all reals. That graph, okay, everybody, that graph is still going through 1. and it still doesn't have a y-intercept. So there you go.
Create a logarithmic equation in the form y equals a log base b of x, where a is between 0 and 1 and b is greater than 1. Graph the function on the grid below and answer the following questions about your graph.
Okay, so in this question here, I'm just told to create a logarithmic expression where the coefficient is between 0 and 1 and the base is number greater than 1. I don't know, let's say 1/3 log base 2 of x. Why not? Why not? Now, let's graph this thing. Okay, now before I graph this, what I'm going to do is I'm going to change that logarithm part of it. So what I'll enter on my calculator will be 1/3, but I'm going to change that to a base 10 so I can actually graph it. So this will be the common log of x divided by the common log of 2. So that's what I need to enter into my calculator to make this thing work here. So here's my y equals, and I've got 1 divided by 3, and then I will multiply this by the common log of x divided by the common log of 2. Now I haven't changed my window settings, so let's graph that. And again, notice that really looks similar to what we've done before. In fact, that looks really similar to what we did with the log base 10. Okay, really, really similar. So what it's doing here is it's sliding up here. Oh, well, it doesn't matter. It's sliding up here. It goes through 1, and then it really takes its dear sweet time to go out there. Now, I'm not going to get too terribly detailed with this. Anyway, the x-intercept is 1. That seems to be an overall pattern, unless it gets moved up or down. That really does seem to be the x-intercept of every single one of these. Y-intercept doesn't have one. It doesn't touch the y-axis. The domain, as I can see over there again, is it's going to be greater than 0, and the range will be all reals. Okay, end behavior. Now, end behavior, when they talk about end behavior, this is a reference to what's on the left and the right-hand side of the function here. Now, this particular function does not extend infinitely to the left. It stops at the y-axis here. So left to right, this graph doesn't exist until you hit the y-axis, and then just beyond it, it starts. And it starts in quadrant 4. When we talk about end behavior, we're typically referring to the quadrants. Where does it start, left to right? Where does it end? And it goes up to quadrant 1. That's my end behavior, starting in quadrant 4, ending in quadrant 1. And because of how we interpret that end behavior, that honestly suggests a graph very, very similar to this. Something starting in quadrant 4 and going up to quadrant 1 doesn't extend into quadrants 2 or 3 at all, or else we would have mentioned that in the end behavior. So there's the properties of the graph that I came up with kind of off the top of my head here. Now I just chose some small numbers there, but based on the restrictions that we got here, that's really what you would expect to get.
Now we'll take a quick moment here to summarize what we've looked at with logarithmic functions and take a quick look at logarithmic regression.
Okay, so let's just summarize the characteristics of these logarithmic functions that we've come across thus far. It's always going to have an x-intercept, okay, and that really does seem to be overall the point 1, 0. Okay, that's where we're going to cross the x-axis there. Doesn't have a y-intercept. The domain will be greater than 0, and the range will be all reals. Okay, and then the graph's going to look something like this, unless you've got that fractional base, right? Because the fractional base reflected it and it went this way. Notice another point here that actually will show up on the graph repeatedly. If you've got that point, it's going to be the point b, 1. So if you've got if you plug the base in there, so for example, let's say that you had the y equals the log base 2 of x, then you know that you're going to get the point 2, 1 on there. Okay, now we're going to talk really briefly here about logarithmic regression, okay, which is very similar to exponential regression. And honestly, it's just going to be the difference will be the choice of a function on the calculator that we use here. But we got to talk a little bit about what the calculator is going to do as a result. Okay, so when you go through and you're going to enter in your data into the calculator, the equation of the logarithmic regression is going to be written like this. Okay, it's going to be constant plus some multiplier times that thing right there. Okay, now let's zoom in on that. ln of x. That's supposed to be an ln of x there. Now, this is another type of logarithm. Okay, we got to be a little bit more specific here. So remember that if you've got y equals the log of x, we know that this is a common log. Okay, that's a common log. The base is 10. Now, if I write y equals ln of x, this is just another type of logarithm. It's also on the calculator here, just below the log button. Okay, so there's this logarithm there. You got two of them. That logarithm is called a natural log, and its base is e. Whoops, sorry, you can't see that. Its base is e. Now, you might be sitting there going, oh, great, good. What's e? Okay, fair question. E, if you look on the right-hand side of your calculator, notice you've got the pi button right there. Notice that just below that, you've actually got the e value right there. So let's go through and let's take a quick look at that. What is that? So I'll press second divide to access e, and there it is. The calculator just writes the e right there. And when I press enter, it gives me 2.718281828, and now it looks like it's repeating, but it's not. This number right here is a very, very special number. It pops out of calculus, okay, some work that we do in calculus. It's like pi. It's an infinite decimal. There's no pattern to it, okay? So it's this irrational number. It's a little bit more than that, but for right now, it's just an irrational number here. It turns out that it's an excellent tool to use as the base of a logarithm. Now, for our purposes in this course, we're really not going to explore why that is such a good choice. You're just not going to see it, okay? Not here. You really need to be taking a calculus course to appreciate the value of that particular number there. But we can still use it, okay? So we've got two different logarithms now. We're going to have the common log, base 10, natural log, base e, okay? And so the calculator, by default, assumes that you want a natural logarithm. So anyway, most graphic, like it says here, most graphic calculators or spreadsheets provide the equation of the logarithmic expression in that form, the regression in that form here. Now, when we go and enter in our data here, we're going to press stat and then edit to enter the data in, and then stat calc, and then number 9 is going to be that logarithmic regression. And so what we'll do here is let's take a look at an example so you can see how that works.
The data below shows the average growth rates of 12 weeping Higgin cherry trees planted in Edmonton, Alberta. At the time of planting, the trees were 1 year old and all were 6 feet in height. Perform a logarithmic regression on the data provided and answer the following questions.
Okay, so here we go. We got these age of the tree, the cherry tree, and then the height of the tree right here. So we're going to enter this into the calculator. So first of all, stat, edit, and then here we go. Now I've got some old data in there, so I'll go up, clear, enter, up, clear, enter. And now, age of the tree. It goes from 1 to 8 here. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. Done. Nice and easy. Now here's the height of the tree. All right. So 6, 9.5, 13, 15, 16.5, 17.5, 18.5, and 19. Okay, good. Everything matches up there. Looks like I got it entered in correctly. Okay, there we go. So now we're going to quit. And we want the logistic regression equation. So, okay, here we go. I press stat. This time we're going to go over to the calc operation here. And this is the one that we want, the ln reg. Remember, this is going to be a natural logarithm, the base e, that special number e. So we choose that. You're probably, if you're using an older calculator, going to have to list 1, comma, list 2. And so remember, the comma button is the one right above the 7. and I get list 1 and list 2 from going second 1, second 2 here. If you got a calculator that does this, you just really have to press enter until you get down to calculate. And so here we go. So here's our regression equation, and I tell you what, we'll round things to the nearest hundredth here. I don't think it really says here, but to the nearest hundredth, okay, just to see what I've got here. 5.71. So y is going to equal 5.71 plus the b value here. What did I get for the b value? 6.54. Okay, 6.54 times the natural logarithm, whoops, of x. Can't see that. There you go. So 5.71 plus 6.4 times the natural logarithm of x. So now with that in mind, we'll go to the next question here. It says interpolate. What was the average height of the trees at 1.5 years of age to the nearest tenth of a foot? Okay, so we've got our equation right here, and I've got it in the calculator. So what I'm going to do here is I'm going to actually pull that up here. So I'm going to clear this, and if I press vars down to statistics, go over to EQ, okay, there's my equation right there. Everything has been stored in there, and I know we've done this before, so that's why I went through that relatively quickly here. Actually, sorry, second thought, I should probably do that again. So I'll press the vars button right here, vars. I'm going to go down to the statistics menu, because what we did was really a statistical measurement here when we did the regression equation. And over in that EQ menu is where we store that regression equation that we just did. So now the question was interpolate here what the height was at 1.5 years of age. So I'm going to go back into here, and I'm just going to replace that x with 1.5. And there we go. That's the value of the equation, 8.36. So it says to the nearest tenth of a foot. So what do we got here? 8.4 feet. When it says extrapolate, we're going to go beyond that. What is the predicted average height of the trees at 20 years of age? Okay, well, same thing. I'm going to come back in here, and actually, this time I'm going to press second enter, because that will pull up that last thing that I've entered in there. And I'll just go back here and edit it, and I'll just put in 20. Delete the 5 there. So here's extrapolating. And again, to the nearest tenth of a foot, we got 25.3 feet. Good. Now, the next question here related to this says, if the average height of the tree is 12 feet, what is the age of the tree to the nearest tenth of a year? Okay, well, this is a little bit different. Okay, this time I'm giving you the height here. I'm giving you the y coordinate, and I want to figure out what the x coordinate is. So the way we typically do this is we're going to go to y equals, I'm going to delete what's in there already, and I'm going to put that regression equation in here. So again, vars, down to statistics, grab EQ, there we go. And I'll put, in this case, I think it was 12, yeah, 12 feet. And I'll put 12 feet in here. Now when I press graph, it's going to go to this standard window settings. I see the calculator's thinking, but I'm not seeing the 12 here because my window settings don't go up to that. So I'm going to press window here, and we are looking at 12 feet. So I want this to be at least 12 feet. Let's make the Y max here 15, so that I'm a little bit above that. Press graph. There's that 12 feet that I'm looking for. And then there's the logarithmic equation there. I'm going to look for that point of intersection. So second, trace to get me to the calc menu. Intersect. You can't really see it. So what we got to do here is we're gonna bring that up there, that cursor up. So there I can see it now. Yes, I'm on the first curve. Yes, it jumped to the second curve. I just press enter to get past the guess. And we get that our answer here is 2.6. So we can answer from that. This is 2.6 years. And again, maybe just to emphasize, what we did here was we entered y1 was that 5.71 plus 6.54 natural log of x, and y2 was that 12. That's how I did that. And then we found that point of intersection at 2.6 years.
A social networking site tracked the growth of its membership during the first 2 years. The table below represents the data collected. Perform a logarithmic regression and answer the following questions.
Okay, so here we are with a similar sort of question to the one that we had just a little while ago here. So we've got this social networking site. We're tracking the number of growth of its members over the first 2 years. So here we go. Here's the data collected. So number of months, probably the number of users here. So I think we can safely assume that the number of months, this should probably be our x and this should be our y here. Okay, so let's take a quick look. Let's go in here. We're going to fit in our values in here. Again, I'm going to press Stat, Edit to put the information in. I've already got data in there from the previous question, so clear, enter, clear, enter. And now my data here, it goes 1, 4, 6, 9, 12, 18, 24. Okay, here we go. So I will put that in 1, 4, 6, 9, 12, 18, 24. And then my number of users, and this is in the thousands here, okay, you can read that off there, is 3.8, 6.2, 9.1, 11.1, 13.3, 19.4, and then 23.8. Okay, so all my data is in there. And now I'll quit, Stat, over to the calc, and then I'll go down to that linear, sorry, not linear, not linear, logarithmic, the natural logarithm. Logarithmic regression, enter, 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 go through calculate. And so there we go. Okay, so now the question here says, determine the logarithmic regression equation, rounding all values to the nearest hundredth. Okay, well, my A value here is going to be 0.36, and my B value is 6.04. So my equation will be y is equal to 0.36 plus 6.04 times the natural logarithm of x. So there's my equation. The next question says, how many people were on the social networking site after 3 years? Okay, well, number of months being, okay, sorry, x being the number of months here, after 3 years, that's 36 months. So what I'm going to do here is I'm going to quit out of that, clear that, press vars, down to statistics. I'm going to pull the regression equation out of here. We'll go over to EQ, and then I'm going to come back and replace that x with 36. And we get 22.0. Now that's a little odd to me, 22.01. Okay, so it looks like the number of, if I just multiply that by 1,000, it would be 22015 users. Now, okay, if you're like me, you probably had a quick look at that and thought, wait a minute, that doesn't sound quite right, because at 24 months it's 23.8 users, 1,000 users there. And granted, that's true. That's true here. What we'll do here is, I'll show you here. If I turn on my stat plot, okay, if I turn on the stat plot, and then press zoom number 9. Let's take a quick look here. Oh, sorry. Whoops. Stop. Sorry, I forgot. I got to put in the new regression equation. If I put the regression equation in here and graph it, okay, if I graph that, yeah, notice that those 2 points up here are a fair bit out of whack, okay, with the data that we're getting here. So that's why you're getting a predicted value here that's less than the one that came up here. And remember, once you get kind of past that big arc there in a logarithmic function, it grows very, very, very slowly. Now, the next question here says, if the growth rate continues, how long to the nearest tenth of a year will it take until the social networking site has a membership of 30,000? Well, I've already got this thing graphed, so here we go. Let's plug in 30,000. Now, I suspect if I press graph, I'm not going to see that 30,000 show up, because I suspect that the Y max isn't big enough. So let's go to our window settings here. Yeah, this needs to be above 30 for this to work here. Oh, whoa, I just realized I screwed that up. That's got to be 30. Sorry, not 30,000. Sorry, I can almost hear people yelling at me through the internet there. That's wrong, you screwed that up. Okay, yeah, but I caught it. So there's my window. Let's make the Y max equal to, I don't know, let's make it 35 so we can see everything for sure. There's my function coming along there. Everything's growing happy. Oh, we're not even close to connecting here. So let's go make our X max here. That's 26. Let's make that a lot bigger. Let's double that. Maybe that'll work. That still looks like a substantial jump here. So let's go back up to our window. Let's make this 100. Okay, that's still not doing it. let's go back up to here. Window. Let's make that 200. Let's just go for the gusto here. Here we go. That's got a cross there. Hey, you think about it. And there it is. There, we finally got a cross there. Now, whoops. So second trace, we're going to look for the point of intersection. Am I in the first curve? Yep. Did I jump to the second? Yep. Pass the guess here. So we're getting 134.96. Okay. Okay, I think we can safely say that that's 135 months. 135 months. Now we want to write, whoops, we'll write that in terms of the nearest tenth of a year. Okay. So once I'm here, I can quit. Oops, quit. But if I pull X up, just press X, that's the number that we got there, and now divide that by 12. And there we go, 11.2 years. So this becomes 11.2 years, and that's where we're getting the 30,000 users. Okay, so there you go. So just a little bit of an exposure to, an introduction to logarithms, common logs, natural logs, and logarithmic regression using the calculator.